So yeah, hi everyone. Good afternoon. I'm Sagar Dharia. Work with Neeraj on BMC in Microsoft. So today we'll be giving you an update on the Linux Foundation OpenBMC, like where things are over there, and then Neeraj will be talking about a work group where we are working with the community on platform telemetry and health monitoring. To give you a brief overview about OpenBMC, this is more like a standard for defining the baseboard management controller stack, and then as you know, BMC is used in various environments. It's used on enterprise, cloud scale data centers. So it's very important to have like a homogeneous stack going forward, and then having an ease of customization in choosing the build based on the embedded BMC functionality. So for that, Yocto, Open Embedded, Systemd and dbus are the easiest choices to get it customized going forward. And then for OpenBMC, you can go to GitHub where you will have features, design documents that are in the works that have merged. Then recipes, these are the recipes for various platforms. There's also QEMU recipe. Then you'll have wiki, meeting notes, and then currently there is some work going on for having a robot framework for test automation and CI. With respect to releases, there has been a more standardization now going forward, a standard process. Basically, there are biennial releases starting from earlier this year. So the first release went out in February 2019, and that was the first release as part of Linux Foundation OpenBMC, and then that release was named 2.6 based on the Yocto release that this was based on. And then we recently had a 2.7 OpenBMC release as well. So the process and the notes can be found again on GitHub for OpenBMC. So the 2.6 release, as I was telling, the few main factors over there were the Yocto refresh, the Sol serial overline, the partial redfish support started kicking in, and then the kernel was updated to 4.19. With 2.7, one of the priorities was to get rid of Python for footprint reduction, and then additional redfish support now that a lot of out-of-band communication is using redfish. And then for in-band, there is a movement to go to PLDM MCTP, to kind of get over some of the limitations that IPMI has, like sensor number limitation or the hardware port bindings, etc. So that is started to kick in now. So the PLDM library to implement decoding encoding of messages is there. Then I believe PLDM responder is there. And then there have been design documents for PLDM request, and then PLDM daemon is something that is being worked on as well. So for redfish, a few main features that I would like to underscore are like firmware update, sensors inventory, and then event logging, etc. So again, that is more like a work in progress. So you can always refer to the release notes and the issues to check what has been supported and what is the upcoming release going to look like. So 2.8 is being worked upon, and then mainly it is continuation of what is being partial and finish it off apart from maybe a Yocto refresh, etc. So 2.8 will be available, I believe, first half of 2019. So on OpenBMC, there are quite a few community forums. It's a very active community. Around 27 CCLAs, the corporate licensing agreements, and then around 150 contributors. And then there are certain forums where release planning is discussed, or security working group discussing about static code analysis, or moving forward about how to get signing done, etc. And then we have recently started the platform telemetry and health monitoring work group as well, where we are working with other contributors in OpenBMC to get a more standard model to report telemetry and monitoring. So I'll give it to Neeraj to take it from here, who will elaborate more on that work group.
Thank you, Sagar. Welcome to this talk. My name is Neeraj, and part of Microsoft Azure software engineer responsible for manageability firmware. And in this talk, we're going to focus about manageability telemetry framework that is currently chartered to define a standard model for telemetry harvesting and collection. So let's talk about, before we move to the solution, let's talk about what are the challenges and the motivation that has been to come to the conclusion or come to the current design that we have. And if you see, the first challenge that we have is the diversity of the workloads in today's scenarios that we see. I mean, the industry has seen traditional compute models where there are either compute servers or storage servers. But now with this machine learning AI accelerated workloads, we see a different kind of infrastructure. We see disaggregated systems. We see high performance GPU systems. So managing those systems is really kind of challenging, right? Because the cloud demands that anything that you can't manage, you can't deploy, because manageability is very key to the cloud. So managing these diverse platforms is very challenging. And the second challenge that we have is especially with enterprise cloud, the availability requirements are very critical. I mean, if you have a high dense platform, let's say storage dense platform, and if the drive is dying, you probably want to read telemetry before it really dies, because you're selling a service and your customer is actually relying on that. So that's why the telemetry is very critical there. And third is not a challenge per se, it's an opportunity. Is like, if you see, the BMC role has changed significantly from past a decade. It used to be a very traditional legacy microcontroller. It was used predominantly very basic operations like power on and off. But now if you see, it has become a really innovation engine within the cloud that is used for all control plane operations like deployments, telemetry, diagnostics, right? So all sort of operations are happening with BMC. So this is an opportunity for us. And this is the second perspective of challenges, right? As the cloud grows, we see that we are defining specialized hardware for specialized workloads, as we talked about in the first slide, right? I mean, there are AI workloads. You need high power GPU boxes for that. But you need a standard method to manage them. You cannot have two different interfaces, like one for compute, one for AI boxes. The manageability interface has to remain the same, right? So that's kind of a high level perspective of you might have different family of processors, but the processor error handling has to be same. You might have different BMCs, but you need to make sure that you have a standard methods to measure BMC health. Right? I mean, you have different add-on cards with respect to storage. You've got to make sure that we have a standard, consistent method to read data from these cards. So that's a challenge, for all of us, right? So let's talk about. So we talked about the problems, and this kind of give you a little bit of objective. What are we trying to achieve, right? So this started off with an email thread that took place in about 6 months back, and people were asking very interesting questions. Hey, I'm running BMC firmware. How do I make sure this BMC firmware is running healthy? Okay, I'm monitoring my platform. How do I make sure, this silicon represents different data versus this silicon? How can we make sure that the cloud running behind, the machine learning running behind, get the consistent data, right? So we started brainstorming, and we came up with a community, we came up with the goal, and we said that, okay, let's work together to define a common interface that can harvest the data within the platform. And the second goal is, once you have the data collected, how can you push this data? How can you represent this data in a more consistent manner, right? So with these two goals, so what are the options, right? I mean, the problem statement is clear. So then when we ask around community, hey, so this is the problem, and I guess everybody has to solve it, but how are we solving it? And the most common response that we get from community is, hey, we have custom daemons. We have custom daemon for processors, we have custom daemon for memory, we have custom daemon for I/O, and then once the data is collected, we use our OEM handlers to retrieve this data. That doesn't scale, because especially with this new cloud-aware scenarios where we are defining new hardwares every kind of very frequently, you cannot change. You cannot keep changing your code. You cannot kind of thinking about, okay, how do we manage this box? That doesn't scale, right? So with that, so we talked about the possible solutions. But when we thought, this is where we kind of currently we stand. So we broke this problem into two spectrums. The first was, how do you collect this data? And the second spectrum was, once you have this data, how can you push this data? So on the first aspect, we sort of thinking, we are thinking to use collect D as our mainstream agent to kind of collect the data from the processors, from the memory. So why did we choose collect D, right? I mean, we chose collect D because it's open source, it's written in C, it's been there for industry for a long time, it's being currently used, it supports more than 100 plugins. So we use that. So and once you have the data collected by the collect D as a native engine, then we use a Redfish standard telemetry model to push data outside the system. So you might ask, okay, why did we choose Redfish? So we did a trade-off between IPMI, Redfish, and the other models, but IPMI is very primitive, right? I mean, there are no standard APIs to push this data, so we had to use OEM commands, but OEM is, again, we are going back to square. So everybody kind of voted for Redfish, and Redfish has a standard telemetry model in place that was proposed last year. It has not been mainstream yet, but there are efforts to get there. So the Redfish model is pretty scalable. You can define your telemetry model that this is the data I want to capture, this is my sampling duration I want to capture, and this is how I want to represent my data. And it also provides you capabilities to define your matrix reports, basically how your telemetry is going to look like when it comes out. I mean, like, do you want it to be pushed, or do you want it to be pulled as a cell log? So it's pretty extendable model with that. And Redfish also supports triggers for a use case. I mean, we have seen many times that if your platform ambient temperature goes beyond certain point, you want to start collecting your matrix. So this model allows you to get this data. So let's go back to this. So this is where current system architecture looks like with this approach. So you have OpenBMC firmware that is running on the lowest layer. It's talking dbus to the system component, and then this is where our collect D is going to stand here. It interacting with OpenBMC processes, getting the data, and then it outputs the data into a output format which is optimized for telemetry, right? Because eventually, what is metric, right? Metric is nothing but timestamp data. So the database, which is the round robin database, it is highly optimized for telemetry, right? So then on top of, once you have this binary, we propose to build a librrd, which is again an open source component that we build on, and we will integrate this subsystem with our IPMI, Redfish, or a secondary method that you want to kind of use. So I'm not sure if you have used these systems, but systems like Graphite, that they consume RRD files natively, and they can give you nice graphs that you can use it to represent your data. So I'm going back and forth a little bit here. So this is where a sample kind of telemetry report looks like. In this report that you can see that we are trying to query system power utilization, and we are talking about we want to min, max, and average data over a period of time. And you could see this report, how does it look like? So we also, this is where kind of, current progress is, and we did further progress, and we did a POC. And so we started off integrating collect D as part of OpenBMC. So we started with 8 mega footprint, then it was further shrunk to 2.4 gig. And with respect to memory consumption, right now it takes about 5 meg of DRAM. And with respect to the storage utilization on the log files, it takes about 23 KB of footprint for about 30-second sample for whole day, about 23K. So that's pretty good improvement on that. So with that, I think I would, this is again a very interesting forum. We are seeing a lot of involvement from community. So I would request you to kind of join this, take a look, get involved, and take advantage of that, because we believe that this is not just problem for us. I think every cloud vendor and every player in this field has a value to add there. So there's a work group call. There's a work group meeting that happens bi-weekly. It's Tuesday 9:30 a.m. PST, and get involved. And there are the requirement sheet that we have put together, and this is very useful for us, and we have really benefited from it because we understand where are the pain points, because we had multiple choices, right? And then we tailored our options based on the choices, based on the response that we got from the community. So there are some good points there, and there are a couple of design proposals that we already have from community. So request you to review that and provide your feedback. And with that, this was it. And if you have any questions, feel free.